All right. Welcome, everybody. Today, we'll be doing more on pencil and paper, as well as tablets. So I apologize for not having an intro lead song today. I didn't prepare one in time, but we're going to jump right into it. And again, this is a pencil paper tablets day. We'll be looking at two concepts, one that you've read about, but we haven't really practiced or applied, which are relational operators. We'll learn some Boolean operators as well, and what that means, and then get into a really exciting topic, which is conditional control flow. And to preview where we're going with that, this is going to give our programs the ability to behave differently depending on circumstances that exist at runtime, or depending on inputs that the user provides. Up until now, all of our programs, when you ran them, if you provided an input, they would flow in one way. And we'll have some more control over that today. A couple of quick announcements before we get into it. First, really pleased to report you all crushed Quiz 0 by and large. The median was approximately 85%, which is a really healthy place to be, especially for having taught functions and function calls. Again, this is one of the most detailed, process-oriented concepts in the course. We're going to hand these back by tomorrow. We're still wrapping up a few loose ends with finalizing the grades. But if you missed anything, please be sure to review that immediately. Right? These are fundamental concepts that you're going to see moving forward. This is a cumulative course. The things that we learned in the first unit, you'll see throughout the rest of the semester. If you're not sure about a correct answer, you want to talk through the concepts, please come see us in office hours. This is some of our favorite work to do with you in office hours. Having a conceptual question about something that didn't quite come together for the quiz, and making sure you've got clarity on that concept coming out of office hours. And I realize that I've got a cutoff sentence here. If you don't know what a correct answer, or don't know the correct answer, or don't understand the correct answer, we're going to ask you to refrain from asking this in a regrade request, right? So the other reason to look at your feedback early and that we limit regrade requests to 72 hours following the release is to be sure that you've got that feedback as soon as possible and that you understand what went wrong. But again, please don't use regrade requests for asking questions. It's much more productive to talk through those questions in office hours, and you know we've got quite a ton of availability. As for exercise 0, the deadline was last night. I received some emails and had a few of you come up just before class with submission issues that came about right at the deadline. Maybe a file was misnamed and it was you weren't able to get it done in time. It's totally fine. Don't stress. This is why we have the insurance points. If it's still not going for you by today, if you still haven't gotten 100%, please also come see us in office hours for this today. We've got a lesson that will go out just following class. This is a reading, and it's a short reading. It introduces to you some of the more detailed concepts of strings. You'll learn about Unicode, which is a way that we're able to represent characters from other languages, such as Japanese, Chinese, Arabic, and so on, as well as emoji, which is very exciting. We'll start to be able to have emoji in our strings in our problem sets. And you'll learn a concept called f-strings, which is much more convenient to use and much more pleasant than the concatenation we've been doing so far. But it's important to learn concatenation before using what we call format strings. And this will be, again, a short reading with some questions on Gradescope due tomorrow. Lastly, the TAs implored me to talk to you about ChatGPT and Google. And we saw coming into this first deadline yesterday instances of concepts that we haven't talked about in class and that some of you who brought the code in weren't able to explain and weren't familiar with. This is probably a key sign that maybe you saw something on Google or ChatGPT that looked plausibly like what we've been doing, but maybe had some elements that we didn't understand. I'm going to ask you for the purposes of this course to try and refrain from making use of these types of resources for exercises. The struggle that we talked about on day 0 of wrestling with a problem and trying to take the concepts we've learned and apply them is how you gain mastery over these subjects. And so if we see code that has concepts that we haven't covered in class yet, that's not the appropriate time and place to try and teach those concepts because they'll come in due time if we cover them at all in this course. So what we'll probably do is try and bring you back to let's walk it back to a minimum state of what would we know about and try and go from there, right? But the only way to do well in this class and to perform well on the quizzes is to master the concepts that we've taught about. All right. With that out of the way, a quick overview of where we're going. We'll be looking at relational operators, logical operators. Got really exciting control flow statements, and I'm hoping that time permits us to try looking at a really beautiful, foundational, exciting algorithmic concept, which is defining functions which can call themselves. We're going to start with some warm-up questions. So I've got some sample code on the left. That sample code actually involves a keyword that we haven't seen yet, but I'm going to let you try and reason through it. There should be enough context, and 4 questions to work through. So I'm going to encourage you to work through these, write them down on paper. The TAs will be circulating around if you have questions. Talk to your neighbors about this, and let's spend about 6 minutes on this first set of warm-up questions. 2 more minutes on this problem. 2 more minutes. More seconds. 30 more seconds. All right. For this very first question, who wants to take a stab at addressing which of these 2 function call expressions is correct and why? All right.
Okay. For number 1, the answer is B, because in A, you would be evaluating a Boolean, and age next year takes an int.
All right. So when you say, and I've taken the die from you, you'd be evaluating a Boolean, where would that actually be? Yep. So is 21, I believe where you're going with this is 21 is a function that when we look at its signature, we see that its return type is a Boolean. So we would expect this to evaluate to a Boolean value. And then we would also expect, well, when we go to check the correctness of this call to age next year, it has this parameter named age, and we need to check to make sure that those types match up. Well, when we look at that, we see that age next year is expecting an integer, not a Boolean. So A is actually an invalid option. And the response was B was correct. And let's look at why. So here, is21 is given an age, which is an int. That's great. And this age next year is given an int, and its return type is an int. So if we work our way out from that, we expect age next year to evaluate to an integer, right? So that's the return type that we're being told. We're giving that integer to the age parameter of is21. That checks out, and that's OK. Right? So this ability to look at a function signature and see its return type and know that a call to that function is going to evaluate to that type, as well as the ability to look at the parameters that are expected of a function call, their types, and what are the arguments that we're giving it, is important for being able to reason through what is a valid way of, in this case, composing 2 function calls. Questions on warm-up question 1? All right. Anyone want to take a stab at 2? And we've kind of alluded to this, but I tried to be a little bit ambiguous about it so that there's an opportunity for someone to respond to this. All right, another volunteer here. This classroom, I'm a little more cautious about throwing the die. Here you go.
I would say A, because as we saw in number 1, we focused on age next year first and then went out.
Absolutely, you're correct. So for similar reasons to our PEMDAS order of operations and looking from the innermost parentheses and working our way out, in order to So we know that this one is the correct expression for making this composed function call. In order to know how to set up our frame for is21, we first need to know, well, what is the age argument going to be? And so we need to work our way from the innermost function calls out. This was something that we saw some confusion with on the most recent quiz. Some folks tended to work left to right, starting from the outermost function call. And it doesn't really come together that way because, again, in order to know what value to pass into this function definition of is21 for age, we must try and understand and compute a final value for age next year, given the rules that we've been learning. All right. Anyone want to take a stab at what's the printed output of evaluating is21 with age is assigned 21? All right, I'm actually, you've got a laptop there. I'm not going to throw it and hit your laptop. Here we go.
It's gonna print out n is 21 because on line 6 it says print n is 21 when you call is 21.
Absolutely, and I'm going to give you a chance to also talk through 4.
It's gonna print out true because 21 is equals to 21, so it's gonna print out true.
Awesome. So those are both absolutely correct. Another confusion on the quiz was the difference between print and return. For printed output, and we'll get a chance to practice this again in one of the upcoming diagrams, when we call a function, and so we have a function call here is 21, followed by parentheses, and an argument age is going to be assigned 21. That's going to jump us into the print function definition. As soon as we encounter that print statement, in is 21 would print. And then as was reasoned, because age is equal to 21, this would ultimately return true. We haven't talked about the OR operator yet, so we'll reason through that in just a moment. But great work on this. As a brief reminder, and we'll see some of these symbols as we're moving forward, you read about these symbols a few weeks ago, 2 weeks ago, for comparing two values. So comparing an integer and an integer, or a float and a float. We call these relational operators because what is the relationship between two values? You're used to seeing these in mathematical notation, right? So greater than or equal to, less than or equal to, and so on. These types of symbols tend to be pretty difficult to type. You have to go look up what's the key code or search the internet and copy from some website, what I often do. Same with not equals. Well, in most programming languages, Python included, these more nuanced symbols tend to be written in a linearization of the idea. So greater than, equal to, right? Less than, equal to, not equal to. And the order of these symbols is important, right? So you cannot write equal, greater. That is not the symbol that will represent the same concept. So the order of these is important, but these are concepts that date back to elementary school for you all, thinking about number lines and relationships between numbers. These operators go between two values of the same type, but I've got an asterisk here. Because if you compare an int and a float, similar to an operation that, like an arithmetic operation that operates on an int and a float, the int will be converted to a float so that the comparison works out. Right? These relational operators evaluate to Boolean values. Right? So it's either true or false as a result of calling one of these operators. So with that quick refresher out of the way, I want to again turn it over to you all. And let's spend 3 minutes on this one. With your neighbors, try and work through what you expect these expressions to evaluate to. And then there is a side question on expression A. Conferring with your neighbors and talking to one another. Compare your notes. One more minute on this. One more minute. Thirty more seconds. 30 more seconds. All right. Who wants to take a stab at number 1? All right, I'm throwing the die.
True,
Why?
because 7 is greater than 3.
Because 7 is greater than 3. All right. Can you make it back? Oh, we got a soccer player. All right. 7 is greater than 3. So let's simplify this down a bit. So we've got 1 and 2. That would be 3. 3 and 4. That would be 7. And 3 less than 7. True. Now, this sidebar question is an important one because sometimes here it's potentially ambiguous. You could imagine a strange world where the less than operator was actually higher precedence than addition. But if we did that and we imagined this first, right, it would be a little bit nonsensical when we think about the types, where 2 less than 3, we expect that to be a value of true, 1 plus true. As we learned previously, the relationship between Booleans and ints is a little bit more nuanced than to say that you can't make some operation at all, and we have to be careful of this. But in general, it's so common and convenient that you would want to put some complex arithmetic expression on one side of a comparison or relational operator or the other that most programming languages I've ever seen, in fact, I think every programming language I've ever seen, ensures that the precedence of less than or other relational operators is beneath arithmetic operators. And so we could have made this a little bit more explicit by surrounding this in parentheses, but in general, you can reason through this by looking at it. Right? How about B? Anyone want to take a stab at B? I saw some interesting takes on this in the crowd. I'm not throwing it to you with a laptop, but.
Type error?
Type error. In fact, this is not a type error, but that's an interesting question. Does it seem like you should be able to compare 2 strings?
No, because they're strings.
All right. That's a fair initial assumption. When might you compare 2 strings in say, an index of a book, or sorry, a keyword index of a book? Alphabetical, right. And so we'll see later how we might sort a large number of strings. And in order to sort things, we probably need a way of comparing them. And so our programming language is trying to be helpful here. And it's going to compare these a little bit more nuanced than just straight alphabetically or alphanumerically. But for our purposes in this very simple example, it would be alphabetically. And of course, what do we expect? True. Right? Because U is a greater, has a greater ordinal in our alphabet than D. That's the only reason here. Now, I saw a really interesting take from the audience, which was false on the rationale that this had 3 characters, or had a length of 3, and this had a length of 4. If you wanted that behavior, based on what we know, we could have thrown in the len function here as well as here, and that is how it would have performed, and that notion would have been correct. This was a little bit of a foreshadowing. In fact, the reading that you'll be doing tonight and tomorrow gets into the details here, talks about string comparisons, and so on. Yep. Actually, let me give you the die real quick so that the recording can hear you.
Does the string comparison, does it only compare the first letter of each side of the expression?
Great question. Does it only compare the first letter of each side? If these were both U's, so if we imagine that we didn't have the D here, right? So let's imagine the string uke, like a ukulele. We would have gone on to compare the second index, or index 1, and n is greater than k, so it still would have been true, right? And so it would keep going until you reach the end. If they were the exact same, this would ultimately be false if they were the exact same string, because one's not greater than the other. Yep? If Duke was lowercase, I'm not going to go there, but that's in the reading, and it has to do with how we encode these letters. And in fact, I generally, there's a note on here to beware of string comparisons. Your intuitions can and will break down unexpectedly. We'll learn some later ways of ensuring that maybe case sensitivity doesn't matter, but in fact, in these basic comparisons, it does. But that's covered in the reading. And finally, last but not least, 110 as a float is not equal to 110 as an int. Anyone want to take a stab at this one? Oh, wow. All right. I'm going to throw chest pass coming.
I think this one's going to be true because the data types are different.
It's a great intuition, and in many programming languages, this would be true. However, the caveat to be careful of in Python is where you have comparisons between floats and ints, similar to arithmetic, it will convert the int to a float in order to make your life a little bit easier. But yeah, technically these seem like they could be different on the basis of a type comparison. But this is one of those cases where you have to be a little bit careful, and it is OK to make a comparison between a float and an int, and it will work as you would expect. So in fact, this would be false because 110 as a float is equal to 110 as an int when evaluated in Python. Any final questions on these? Yep. Here you go. Yeah.
So if there was a case where on a quiz there is a precedence of the less than sign, would they just come out as an error?
So I believe you're, let me try and represent this here. If we wrote something like this, would that be considered an error? We're not going to be tricky like this. This would, I actually want to go and try this in VS Code, given the type hints that we have. I would hope that it gives some highlights and says, you really shouldn't be trying to do this. And I'm seeing that it would not. But we won't be tricky like that. In general, in fact, where there seems to be some ambiguity, we'll try and be helpful there. All right. Let's actually reason through the logical OR operator. So this operator that you just saw, we haven't talked about it yet. And I've got another exercise here for you to try moving through. So in that function, I'm going to tell you that it generally behaves as you would expect it to behave in terms of the return value. in that if you are 21, or if 21 or greater is passed in as an argument, that you will get a true value out of this. If something less than 21 is passed in, you will get a false value out of this. Given that, can you reason through how the OR operator works? There is one slightly tricky question that'll be an interesting debate among the two of you, or three of you. And lastly, how would you rewrite line 7 using the relational operators we just looked at to be simplified? Let's go ahead and spend a few minutes on this. So it just becomes 1, right? And yeah.
And the thing is because it Python lifts it, like VS Code doesn't actually know that you didn't.
Okay, sure, yeah. It is, yeah.
It's support primitives that like have slightly weird behavior.
One more minute on this. One more minute. Twenty more seconds. I'd love to hear from someone in the front half of the room for how you think this table gets filled in. Someone want to try front half of the room? Here we go. All right. I'm gonna go write it in as you talk to me.
Okay.
All right. So the first one, false or false?
False.
All right. That makes sense. Second one, true or false?
True.
True. Third one, false or true?
True.
All right. And the most interesting of them all, true or true?
True.
True. All right. How many of you said true or true was false? So this is one of the more common misconceptions in the OR operator for first-time programmers. This notion that if you have an OR statement, you expect one or the other to be true for this to be true. It turns out there's a different operator for that. That's called exclusive OR. Exclusively one or the other is going to be true. But by default, in this implementation, and you had no basis for reasoning through this, somewhat intentionally, given the example, I wanted this to be a little bit of a conversation, because I've seen in previous semesters this misconception carrying forward all the way to the final exam, and I want to be sure that we're careful of it here, which is either one or both sides of an OR operator can be true, and as soon as that's true, then the OR will evaluate to true. All right? So in this case, the only way that the OR operator will evaluate to false is if the expression on either side of it, if both expressions on either side of it are false. All right. And lastly, how would you rewrite line 7 to simplify it using a different operator? Yep.
It would just be age is at least 21, so age is greater than or equal to 21. Or, yeah, return, and then.
Great. So this is one of those examples. We've talked about expressions giving you some creative flexibility to express the same idea in multiple different ways. In this case, we were verbose and involved more operations than we needed to say your age is equal to 21 or greater than 21. As we know, we've got an operator that conveniently makes that comparison all in one step using one operation here. Right? What I want to pause on before moving to the next operator is notice here in our usage of this example that either side of this can be an expression. And while we generally, you kind of need to know these identities as something that you bake into memory. They tend to be somewhat logical, but again, the one that you have to be very careful to memorize is true or true is true. But sometimes it can feel a little bit it's hard to motivate why you memorize these rules or why they're important. And the reason is because you have full expressions on either side of it. And so you start to be able to build up complex logic. All right? So following from this, I've got another example that's slightly different. We have the AND operator in a very similar function. I'll let you read through this, and let's spend 2 more minutes on this one, going through it. I'll remind you all that we have excellent TAs in the room. If you have questions, raise your hand. We're happy to come work with you. Thirty more seconds. 30 more seconds. Someone from the back quadrant of the room want to help me fill in this table? All right. I'm going to give you the die, and I'm going to run up. So what do you think about false and false?
It'll be false.
False. All right. Continue with true and false.
It'll be false.
False. False and true.
False.
And the last one, true and true.
True.
Absolutely right. So if we reason through this, and in this example, we'll come back and trace through this a little bit more closely, but you know, if it's true that your age is greater than 18 and it's true that you have an ID, then plausibly you're able to prove you're old enough and are in fact old enough to enter the Cottage Core Club, right? And that's great. But if either of these are not true or both of them are not true, then plausibly you shouldn't be able to enter, and this would return, in fact, return false. All right. Lastly, I want to give you a chance to respond to question 2. What do you think has higher precedence, relational operator or the logical Boolean operator of and?
And because in order for it to be true, both of them have to be true, or else it's going to be false.
You're correct. I'm going to ask you, does the and evaluate first, or do you have to evaluate this to be true or false before evaluating the and?
You'll have to evaluate the greater than or equal to first.
Yes. So when we talk about the ordering of precedence, we'll say that there's higher precedence given to the greater than or equal symbol, or a relational operator. So that will evaluate first, and then once we have the full evaluation of the left-hand side and the right-hand side, we'll then go on to evaluate the and operator. Great work. All right, any questions on this slide? You can throw the die here. Got a question? Lost my pencil. Here we go. All right. I'll try and get you this die. Here we go.
So if it was switched around, like it says return has underscore ID and then and age is greater than 18, would it be higher precedence that way?
Great question. If we flipped these, would the order left to right have mattered here? And in fact, it wouldn't have. And let's talk through why. So the proposition here is return has ID and age greater than or equal to 18. Sorry for going off the slide here. Here as well, we would need to simplify age is greater than or 18 to either true or false, depending on the value of age, before we're able to evaluate and, right? And yeah, and so if we work through this, for example, and we gave has ID, let's say that's true. So I'll just note in true here. And let's say age is 19. When we reach this expression, or this return statement, and we look at its expression, we see this and we think, okay, before we can actually evaluate and, we need to know what are going to be the simplified values of the left-hand side and the right-hand side. So has ID would have simplified to true. And age is greater than or equal to 18 would have also simplified then to true. And it's hard for me, I guess where I would like to encourage you to think is how could you have simplified that and to know whether it's true or false before figuring out whether or not age is greater than or equal to 18. And you kind of get stuck at that point and realize, oh, I need to go figure out whether or not this is true or false. And that's the intuition for why and needs to resolve after the relational operators. Great question. I want to point out one other very common misconception in the early days of programming, which is, notice here we have this has ID. Its type is Boolean, and we're using it as the sole right-hand side operation here. Notice, or operand here. Notice that I did not need to say has ID is equal to true, because this is redundant, right? We don't have to compare whether a value which either itself must be true or false is equal to true, because it itself is either going to be true, in which case that's true, or it would be false, in which case it's false. So we're able to use Boolean values as Boolean values in a relational operation, or without a relationship to is equal to true or false. Yep. Go ahead and call it out. I'll repeat it.
If you have, for example, both an and an or, do you just read it from left to right, or does one have precedence?
Reasoning through the logical not operator. So the question was, what's the precedence between and or? And because the not operator tends to be so straightforward, I wanted to make this example and the second part of this question a little bit more interesting, and to give you a chance to try and reason through this. What is the precedence between not and or? It turns out part one of this should be very straightforward. I hope that it is. And then part two, given the context, we might be able to reason through as well. But let's spend 2 minutes or so on this one, and then we'll move on to conditionals. All right. The last question here is actually pretty silly, so let's talk about this. And it's not necessarily straightforward how you would determine it from this example. But let's start with what's most important on this slide, which is not true and not false. On the count of three, what is not true? 1, 2, 3. All right. So the not operator is the most straightforward of them. I'm not even going to do the same with true. Not false is true. But things get interesting, and this isn't. This is a particularly silly example, but it does show you where it's. In fact, this is a bad example because it is kind of ambiguous. How should this be broken down? What is the precedence, as was asked in the audience, of not versus and versus or? And here we can get a sense that the not operator is probably the highest, but we don't have a sense of whether and or are, right? So the not operator is going to tightly bind in this way, right? And then it turns out that the and operator has the next highest precedence. So in this example, it does work left to right. But in general, if we had switched and put looks really old or not age is greater than 18 and has ID in front of this, it would have worked in a similar way. So you do want to be very careful with this. In general, if you have complex Boolean expressions in this course, you should not write them like this, right? Use parentheses to make it very obvious and explicit as to how these binding rules apply. As you become more comfortable, there might be cases where you can avoid using parentheses, but when in doubt, use parentheses to make the evaluation of your expression more legible. For reference purposes, I've got on the slide deck these tables that we filled out. For now, we're going to assume that we'll learn there's some more detail to this, but for now we're going to assume and trust that in what you see in this course, these logical operators for or, and not are going to have Boolean operands. The truth is a little bit more fuzzy than that, but we'll get there in due time. All right? In terms of precedence, when you're reading these expressions, arithmetic, relational, not, and, or, in that order. But in general, this is a lot of rules to remember, and you can simplify your life and make your code a little bit easier to read by using parentheses where possible. All right. So because this is in the slide deck, I'm going to continue on to a really exciting new topic. And before we introduce the syntax that you're looking at, because Python is so beautifully legible, I want to give you a chance to try and see some new code that you've never seen before, see a concept that's new to you, and try and reason through it. And so the start of our slide deck alluded to, it was some public domain imagery of 3 bears. And if you know the story of the 3 bears, this hopefully rings a bell. Let's spend a few minutes with your neighbors trying to reason your way through this example. Remember, these are string values, so try and write them as string literals for good practice. Thirty more seconds on this one. 30 more seconds. All right. Who wants to take a stab at number 1? What do you expect the return value of taste porridge with an argument of temp is assigned 175? All right, from the audience here.
For 1, I said too hot because it's 175, so you would look at the second temp, second
One
if
second,
statement.
hold tight for just a second. Too hot is what we're propositioning. And okay, take me with you.
So do you want me to explain why?
Yeah, that'd be
Okay.
awesome.
Yeah, so too hot, so since the temperature is 175, I looked at the if else, like the if then else statement. So the first one is temp equals 140, so that's not it. So I looked at the else, and then temp is greater than 140, which does make sense. So then that would return us too hot.
Fantastic. Round of applause for that explanation. Appreciate you taking us through it. So we haven't seen this yet, but it hopefully does feel somewhat familiar and not too much of a stretch. Anyone want to call out what the evaluation of temp, the argument temp being 110 would lead to? Too cold. And I forgot an exclamation point there. It's a very exciting time to be in this class as we're learning conditionals. And lastly, 140. Just right. All right. One of the common experiences you'll have in programming as you're learning new things is encountering something new for the first time. Hopefully it's as legible and readable as this, but sometimes before you learn all the details, it does help to try and load it into your brain as to what's going on, what is a use case for this. And I want you to realize that here we're seeing something that's entirely new that you could not express in your programs based on what we had learned so far, which is we can call a function and we can vary its input and decide, make decisions based on what we return off of that. Previously, we could only perform direct computations. And here, we're able to make and introduce Boolean logical decisions. So let's look at what an if statement is, and I'll learn a little bit more about it, and then try practicing it. So in the simplest form, an if statement has the keyword if. Just like def, if is a keyword that is built into the language that you can't use for any other purpose. It serves this sole purpose, right? It's going to be followed by a Boolean test expression. And again, What's so beautiful about expressions is that that's where we have the creative freedom to express, in this case, the logical conditions that we want to express for our program to decide to do one thing or to not do that thing, right? So on the right of this slide, I'm going to show you visually how we tend to represent these in flowcharts. And when we have a conditional statement in a flowchart and we try and think about this graphically, we often represent that as a diamond. And a diamond is sort of a fork in the road. We have this decision to make. Which way do we go? Well, if that Boolean test expression is true, like you all just reasoned through, then we would go into the then statements, right? I'm eliding these. We're just using some pseudocode where we have a few dots and then statements. This is, of course, not valid code. But you'll notice that it is indented. Just as you all learned that function definitions have a level of indentation for their function body, here we could call this the then statements block or the then statements body. And it also needs to be indented, as you saw in the previous example. This establishes the relationship that this code is only going to run if when control or when the program reaches a state of execution that we test, is this Boolean expression true or false? If it's true, we would then go into the then block. If it was false, we would skip over it. Right? This is the simplest form of an if statement. You'll notice there isn't an else like we saw before. So this gives us the ability to make a test, and if that test is true, then the Boolean expression evaluates to true, then we would do what follows indented right after it. If it were false, what we will see is we actually skip over that then block. So if that Boolean test evaluates to false, we don't go inside of that those indented statements. We skip right over them and go to the statements following. Right? The form that you saw, in fact, you saw 2 examples of this in the previous form, is a little bit more nuanced when we want to decide sort of a fork in the road. If something's true, do one thing, and if it's false, do another thing. And if it's one or the other, we're not going to do the other. So if the Boolean test expression is true, just like with before, we would go into the then block. But when we add this else branch or statement, you'll notice that this is also a keyword, followed by a colon, and then our code will once again be indented for the else block. Here, if our test expression is false, we would go into the else statements and perform whatever is done there. And so notice this gives us a way of choosing, based on some Boolean condition, to take one set of steps if something is true, and another set of steps if something evaluates to false. Before we practice this in a tracing exercise, any questions on what we're seeing here at a high level? All right. Again, these are in the slide deck for reference, so I'm going to go right on to a diagramming problem. So this is a sort of a silly diagram where we get to practice this conditional flow. And here we're going to see a function that has many statements in it. Previously, you've seen functions that have had maybe a print statement and then a return statement. Here, you're seeing a sequence of if and if-else statements, and they're going to flow top to bottom, but following the logic we just talked through. So this is a chance to try and apply what we just learned, and I'll give you all a few minutes to try and produce an environment diagram to trace this logic. We'll have 5 minutes on this. Oops. Oh, all right. 2 more minutes. 2 more minutes. We're looking for what's in the output column primarily, but also be careful of what the return value ultimately is for this frame. One more minute on this. 1 more minute. All right. I'm seeing lots of correct answers around here. And I'm also seeing some blank output columns. So if you have confusion, let's let this be the time to ask questions as we're moving through this. So I've gone ahead and fast forwarded just a little bit with the things we should be comfortable with. I've set up my globals. We've got our reference from number report to the function definition. And I've gone ahead and actually evaluated line 25. I've set up a frame for the call to number report. I've established the return address, which is the line that function call was in, to the parameter x is 110 in this frame. And so we're ready to go. We reach this very first if-else statement. And does someone want to call out what they think the printed output is? Or what? Let's actually not jump there. Let's be very careful here. What is the result of 110 divided by 2, taking the remainder of that integer division? 0, right? So here we have the evaluation is 0 equal to 0, true or false? True. Because this is true and this is an if-else statement, we will print even. So the output will have even as the first line of output printed, right? Do we print odd? No, right. So we skip over odd, and that's the semantics of, we skip over odd, and we don't print odd, right? Because that was in the else branch, right? So if we have a true statement and a true expression in the if, we'll go into the if then block, we print even, and then we skip over what's in the else block, all right? We then reach an unadorned, or just a plain if. And so here we're asking, is 110 evenly divisible by 3 is another way of breaking this down. But if we divide 110 by 3 and take the remainder, is that equal to 0? True or false? False. 110 is not evenly divisible by 3, sorry. So we skip over this entirely. We don't print that. And lastly, we reach an if statement. And what I want to encourage you all to do is read these top to bottom. Try not to reason ahead or look at the entirety of this block. Just start from the top and work your way through it. So first we ask, is 110 equal to 0? False, right? So then we look at, is there an else branch connected to this if statement? Yes, there is. So we go to the else, and we go inside of it. And then we ask, is 110 greater than 0? Yes, true. So we print positive. And we skip the connected else branch here. And notice that we know that that's connected. VS Code will actually try, and it's very faint on the slide, but you'll see it in your editors, that this line that VS Code puts in is related to the indentation. And so that was the connected else. We're done with that. We're done with that else statement. So finally, we're going to print x is, and then concatenate the stir value of x, which is 110, right? And are we done? No, not quite, right? So this is one of those cases where we have a funny function. And you've seen this once before. But here, if we wanted to be explicit, we could have dropped in a statement that is return none. But generally, this is implicit. And so in this case, we always have to finish out a function call before going back to where we came from, or before our function, or before our program has completed. So we're going to enter a return value, in this case, of none. That would take us back to our recorded return address of line 25. So now we're back down on line 25. We've just completed this function call expression. There's nothing else for us to do, and this would be the end of our program. Questions on this example? I'm not seeing it. Wave the hand. Oh, all right, way. Great. Thank you, TAs with the eagle eyes. All the way back here. I'm going to throw this to you.
With the return value, did you have to write none, or could you have drawn like a circle with a line through it?
Circle with a line through it, also representing none. In Python, this value is indeed the none value. If you were to have printed this result, you would see none is truly the return value, and none is a proper value. I'm going to encourage you to use the word none in this case intentionally here. Great question, though. In some other languages, you wouldn't know what to expect necessarily, and a null value or nothing, in fact, some of these, it's beyond our concern. But yeah, great intuition. Can you have an if-else where it says return instead of print? That's a great question. We're not going to have time to move through this particular example or the following example. Both are very fascinating. We'll come back to these. But you'll notice in both of these examples, we do have if and then a return inside of it. Now, what I want to actually encourage, let me go back to this. Dang, hold on, sorry. Keynote's lagging a little bit. In this example, if for some reason we had written in this case, and we'll have examples that practice this because this is one of the key differences between return and print, and it becomes important as we get to more interesting algorithms. But if we had replaced this with return, the string even, well, let's just do return none. Like, let's just say we want it to be done. What we know about the return statement, right, is as soon as you reach one, that function call's job is complete. We would return none, and none of the rest of this function would evaluate. None of those other print statements would evaluate. So this is possible. There's not really a good reason for that in that example, but there is a good reason for it in the examples that we have in the slide deck. I want to give you just a moment to look at this example, and I would love for someone to tell me something that they think feels a little uncomfortable but interesting about this example. You don't have to try and diagram it. We don't have time for that, but just take a look at this code and what feels interesting about it? Here we go. I'm going to give the die here.
Is it that the third parameter just there's just nothing there? Like,
interesting. So one interesting thing is we have an empty string, which we haven't really had much use for so far. It turns out the empty string is a valid string literal. It's just a 0-length string. And it's useful for being a starting point for building up larger strings. But you're right, that's something interesting. I saw a hand over here. Here we go.
It loops through itself unless you finally return dest.
It loops through itself until you finally return dest. Notice there's this really fascinating return statement here. And what function is this return statement calling? It's calling rev, right? And so this intuition that it loops through itself until finally we reach some condition that stops the looping in this case. And we'll learn some more terminology around this, is exactly the right thing that seems interesting and fascinating about this. This is a function that's able to call itself, causing a repeated behavior. And one of the things that's interesting is the number of times this function will call itself is dependent on the length of the string we give it, in source. This is one of the first true algorithms that we see where we have a fixed length amount of code that will wind up evaluating and sort of looping through its iterations of, or recursive evaluation would be the more technical way of saying it, but we'll get there. And so if we had a really long string, your environment diagram would have, in fact, one frame per every single character in that string. We don't have time to move through this, but I wanted to leave you with something to reason about and think about. And if you want to try diagramming this, you have all the tools you need right now to work through both of these examples, actually. They're somewhat related to one another. But we'll come back to these on Thursday. Great work today. And you've got the lesson that's out.
So no all hands today?
Yeah.
Okay.